Okay, this should be a relatively short lecture today, but I want to get something in, even though we're going over the midterm today as well. And since we lost a couple days due to snow, I want to make sure to keep moving things forward here. All right, so today we're going to talk about information transfer, and we're moving into the networking part of the class where we're going to deal with sending things over the network, and this is where packets and protocols and transferring large amounts of information start to become important. All right, so previously we looked at error detection and error correction methods, but for those to be useful, we need to be able to do something with that when we detect that there's an error. In other words, we need to decide how to encode the redundancy needed. That's part of error correction and error detection. And but we also need to decide what to do when an error is detected. In other words, when I have an error, what do I do about it? Do I re-request a packet? Do I just throw it away silently? There needs to be some set of rules we use to do that. Now, a simple approach might be to send the entire message and then check it for errors, but a lot of times that's unwise or impossible. In other words, imagine you have a really large file. Let's say it's a 500 megabyte file that you're transferring, and you transfer the entire file, and then at the end you say, does it have an error? And if it does have an error, then you might have to re-request that the entire thing be resent again. And so the question is, why is that unwise or impossible? And the answers are, to that question, why not send all the data and then check, is that, well, first off, streaming data can't all be sent before checking. It's coming in as it's coming in. So you need to check it on the fly as it's coming in. The other thing is, if we find an error in a single check of a large message, then the only recourse at that point is to say something went wrong in this 500 megabyte file. I guess I'll have to re-request and get the entire thing again. And that can be wasteful because really it might just be one part of it that got corrupted. So why have to go through the hassle of resending the entire thing? Also, some error correcting codes or forward error correcting methods only work with fixed size blocks of data and not on really large, arbitrarily sized messages that are 500 megabytes large. So the end kind of motivation here, the end result of that is it's beneficial or sometimes necessary to divide a large message into these smaller chunks. And that's what we're going to refer to as a packet. So in other words, if you have a really large message, you divide it up into smaller chunk sizes called packets. And that is because of either it's necessary to do that, like the wireless packet size has a maximum, or the network packet size has a maximum size, or it might be because it's just more it's beneficial to do it that way, because that way you don't have to resend the entire message if there's an error. You just have to send the one packet that was bad. Now, what makes a packet? What do packets usually have? They usually have some sort of header information, which is data about the packet itself. They have a data section, which is the actual data that is part of that packet. And they have some sort of check value, CRC check data. It could be the redundant data need to verify the message, or it could be redundant data for the forward error correcting code to work. So think of a packet like you would an envelope that has a letter inside it. You have stuff written on the outside that tells information about the packet itself. Where's it going? Where's it coming from? Maybe it has something about what type of information it is on the outside. And then you open it, and there's the data on the inside. But it goes one step further to have this check value that says this is a summary or redundant information about what's inside of that. Okay, so let's focus on the packet header here for a second. The packet header is going to generally contain information about that packet, such as addressing information. Who's it going to? Who's it coming from? Just like a return address and an address on an envelope. There also might be a sequence number associated with that says this is packet 1, this is packet 2, this is packet 3. So that way, if a large message gets divided up into smaller packets, you can make sure the order is correctly preserved and none of them were missed. There also might be a version information about the how the packet was created, or what type of packet it is, what version it is. And there could be some other stuff there as well, depending on the kind of network or the kind of communication system we're building out of that. Now, again, think of that information like stuff that would be on the outside of the envelope that is wrapping the actual data. The data section, it could just be the data. It might be the data that's encrypted. It could be the data that's has forward or error correcting code information applied to it or in there. But the data part of a packet is often called the payload. It's like the actual message that's being sent that's wrapped inside of that packet. So think of that like the papers or pages of information that are inside of that envelope that's being transmitted. Now, the check value or check data section, that is some sort of value or other, maybe it's larger than just a single value, but it's data used to check the integrity of the data portion of the message. Usually it's a CRC of the packet data. It might be a block of forward error correction data. It might be both the CRC and forward error correction data. It might be, it may also include not just the data, but also the header of the packet. But the whole purpose of the checksum or check data, check value, is to ensure the correctness of the packet itself, the data that's in the packet. So, because when you receive a packet, you don't want to take an action on it or use it if it's bad data or it's corrupted in some way. So we check to make sure of that. Usually it's a CRC. So here's a picture of what we're talking about. Here's this is a packet. We have the header, we have the data payload section, and then we have the check value at the end. Now there are a couple different methods for creating packets like this. That notice that this payload could be, some packets might have a lot of data inside of them. Some of them might have a very small amount of data. So there are some methods of knowing, how do we know once we've started reading the payload when it's done? How do we know when we're at the end of it? So in other words, this is just bytes of data that we need to read. How do we know when we get to the end of that and it transitions to the check value? And the answer to that depends on the system that we set up for creating our packets. And there are really several different options. One of them is fixed size packets. In other words, every packet is the same size. So for example, you might say the overall packet size is always 128 bytes or always 32 bytes. It's always the same size. It's fixed. There are also what are called data delimited packets, where there's a special character that ends the end of the payload section. So in other words, you might have, think of that like quotation marks. You say it starts here and it goes until we get this end quotation mark over here. It might be a null character. It's read data until you get to a 0 byte. And each of those have kind of advantages and disadvantages. We'll talk about those here in a second. But there's also what's called a size field delimited. And what size field delimited is, and that's that has a value in the header that says how long the data payload is. So in other words, it might say 128. And if that's the case, there are 128 bytes here before it goes to the check value. Or it might have 5. In that case, there's 5 data bytes here and then the check value. So what are the advantages and disadvantages of each one? Well, fixed size packets, obviously the disadvantage there is it could be wasting packet size and transmission time. If you only have 4 bytes of data to send and you have a 128 byte packet, you're wasting all that time sending junk and you have to kind of pad that in some way. Also, that could be problematic because we don't know when where the data ends and the padding begins in some cases. The advantage of fixed size packets is it's very simple. They're always the same size. We always know where the check value is. This is just data. So it's simple in that we don't have to worry about allocating different amounts of data or memory based on different packet sizes. It's always the same. You can do static allocation. There are also data delimited packets. The disadvantage there we kind of mentioned was if you have a delimiter, like a null character, that means null could not appear in the data because it would be accidentally interpreted as the end of the packet. The size field delimited is probably the most used and the most generic because that way you can have a variable size here and have it be arbitrary data without having to worry about the delimiter byte appearing in there. But the disadvantage of that is we have to specify the size in the header, which means that we're using an extra byte in the header, or maybe 2 bytes depending on how big we want the packet to be. But we're using extra bandwidth in the header to specify the length of the data that's over here. It can also be useful, though, to put that in the header on the receiving end, because that would allow the receiver to read the header and then allocate the amount they need to store the payload dynamically rather than having it worst case. In most cases, on most systems, there's kind of a hybrid approach used where that's size field delimited, where the header tells us how big it is, but there's a maximum size that it's allowed to be. And that's kind of like how Ethernet packets work, as they are variable size, but there's a maximum they're not allowed to go over. So that tends to be the one that's most used, is the size field delimited. All right, so now that we have packets, we need some sort of set of rules for their use. Again, think about the postal system and mail. If you just had letters, it's not enough. You have to have rules for how they are used, how they get routed, how they get delivered. And the sender and receiver and the system that the packets go across all need to use those same rules. In other words, you put the to address in the middle, you put the return address in the upper left corner, you put the stamp in this place, and actually if you get those backwards, the letter won't go to the right place, it'll go back to you. Or if you put the stamp in the wrong spot, their machine will not be able to detect it and it'll get kicked back out or set aside as a human needs to look at this and figure out what this idiot did with his letter. So we need to have that set of rules. It needs to be followed by both the sender, the receiver, and any system that touches it in between. And well, one thing, note that set of rules is what a protocol is. And I'm sure everybody's heard the word protocol. And if you think about just the word protocol itself, like diplomatic protocol, or it's kind of a set of rules for how you behave or how you accomplish something. You follow protocol. And same thing is true for businesses or the military or anything else, is that there's a certain set of rules you follow for how you go about doing things. And that's what protocol means here as well. So protocol rules that are involved in information transfer are the packet format itself, meaning what's in the packet, where is it in the packet. Again, think of an envelope. Where do you put the return address? Where do you put the address? Where do you put the stamp? How do you seal the envelope? What are the rules on the sizes that you're allowed to have, and postage requirements? All of those rules are part of that packet format. We also have rules for, a lot of times in protocols, we have rules for synchronization, meaning how do we add sequence numbers? How do we make sure the sequence numbers haven't been skipped? Or how do we make sure if it's a duplicate sequence number, what do we do with that? There's also might be rules for connecting. In other words, how does the sequence get started? So in other words, we say, here's some data I want to send you. How do I start that process? Rules for addressing. How do packets get routed and delivered? Rules for stimulating and maintaining flow. In other words, if packets are coming in too quickly, how do you say hold on? How do you say resume? Or if you want to pause the reception of packets, how do you pause that? If you decide you don't want that delivery or that thing, how do you say abort? Stop sending me that. Also, rules for error detection, correction, recovery. That includes both the error correcting code or error detecting code, CRCs, whatnot. It includes that, but it also includes things for timeouts and retries. In other words, if you're waiting for something to happen and it doesn't happen, how long do you wait? And how many times do you re-request something and have it fail before you give up? And that's what timeouts and retries embody. There also might be rules for disconnecting, that after the information transfer is completed, how do you inform the sender or the receiver that now the process is done? That's it. We're done now. So if you think about a book with a whole lot of pages and you want to send that in through to another end in an envelope or a set of envelopes through the postal system, how would you put that back together after it was mailed one page at a time? And the answer to that is you'd have to put the page numbers back in order. You could also think about it like you're carrying a stack of papers. You drop them on the ground and they go everywhere. How do you gather them back together and put them in the same order? And the answer to that is, well, that's where that sequence number syntax and semantics come into play. How do we sequence everything? How do we make sure none are lost and all of them are put back in the same order? All right. Now, like I said, this is going to be a short lecture, but we're going to look at some of these protocols more carefully going forward. But you'll notice that protocols, you could make your own protocol for a lot of systems, or you could use a standard one. And standard protocols are commonly used. You've used some of these probably today in some form or another, but by having a standard for protocols, it allows interoperability, meaning that as long as you design a system that follows a protocol somebody else published, then you can talk to those other systems that already exist that use that. And the entire internet is based on that. So Ethernet, wireless, including wireless variants like Wi-Fi, those have a certain protocol and a certain standard for how you make packets, how you transmit things, how you address things. The same is true for wired networks, so LAN networks. And then sitting on top of that is like TCP/IP, which is a suite of protocols, TCP, UDP, and IP. We're going to look at those in an upcoming lecture, which is going to be, we're eventually going to write code that talks over these kinds of networks. But that's a protocol for transmitting packets where they can route across the internet. So when you do a Google search or go to a web page, log into Discord, there's some sort of protocol of TCP/IP, UDP being used there to do that. And the P in each of these stands for protocol. HTTP, the kind of protocol of which sits on top of TCP/IP, which sits on top of Ethernet or Wi-Fi or some other, might be DSL, some other form of networking. But HTTP is the language of web browsers and web servers, and how do you get a web page into your browser? How do you make the request? How does it get fulfilled? How do the images get in there? How does when you interact with that and type things in and hit submit, how does that get sent? There's a whole protocol involving that. HTTPS, which is the secure version of that, same thing but adds an encryption layer. FTP, file transfer protocol. The post office protocol for email, which is either POP or IMAP, one of the two. There's two different protocols for that are commonly used. Could be other ones as well. Telnet or secure shell log into a command line interface on a remote machine. RCP and SCP, those are remote file copy protocols that are in Unix systems. And then even the GSM protocols for mobile phone systems, there's a protocol there for mobile communication. So there are just tons and tons of these protocols. And a protocol, remember, is really just a set of rules for how you accomplish some sort of communication. And some of those protocols might touch hardware parts of things. Like, for example, GSM. There's a certain way you have to encode the data and hardware you need to do that. Ethernet is the same way. But TCP/IP really can sit on top of other kinds of hardware. So there's no hardware component to TCP/IP or HTTP, but there are hardware parts to Ethernet and GSM, for example. And there are just tons of these protocols. And if we're making a system, we could make our own. Like, let's say we're making an online game. And in that online game, we want to have it be massively multiplayer, where users log in, they interact with things. They have there needs to be a set of rules for how do you log into the game, how do you transfer the data of your keyboard presses and your user input, so that goes to the server. The server then has to send you the game state back. What are the rules for encoding the game state and receiving those input and output rules? There's just a lot that needs to be considered there, and that would be a case where we could write our own. Now, it could still sit on top of TCP/IP or Ethernet. We don't have to recreate the entire internet ourselves. We just need a set of rules that sits on top of that, which is what FTP and HTTP and IMAP and POP, those things can all sit on top of and make use of TCP/IP, but have another set of rules that are application specific, just like a game server. And later this semester, we're going to spend some time looking at like how would you make a game server for a multiplayer game. And we're going to sit that on top of TCP/IP, which is going to sit on top of Ethernet or Wi-Fi. All right, so to conclude here, relatively short lecture, just 20 minutes. There are many standard protocols and many more proprietary protocols. We could use a standard protocol like TCP/IP to do communication, and then we could even make our own that sits on top of one of those standard ones, or we could make our own system entirely if we wanted to. And that's really all I wanted to get covered today. Like I said, it's a relatively short lecture. Hopefully you came to or are planning on coming to the midterm review session to get your exam back. And also I'm going to go over the exam. But going forward, we are going to have some additional labs that are coming up. So make sure that you learn what mistakes you made on the midterm. Because a lot of those concepts that we had there are going to come back again when we get into the networking portion of the class. So where we're going to go from here, we're going to dig into how TCP/IP works. We're going to do some networking stuff. We're going to do a little bit of embedded stuff, hopefully, with the networking with those other little modules you bought, which allow you to connect to Wi-Fi and do socket programming over that. So we will get to that stuff in the next few weeks. We have a little bit of groundwork to lay with networking. Next class, we're going to look at the OSI model for network protocols, which is really, it's kind of a standard way of creating protocols. It's like a standard that defines how you make other standards. And then we're specifically going to dig into TCP/IP programming and look at how do we make a program that talks to another program over the internet, which is what Google and web browsers and web servers and Discord and all kinds of other things are built on top of. The ability to be able to write code that actually interacts with a remote machine and exchanges data. And so we're going to spend some time doing that. Okay, so that's it for today. I'll see everybody next time, or hopefully in class, if I didn't already go to class. And other than that, everybody stay safe, and I'll see you soon. And next week, we're going to really dig into network programming stuff. So look forward to that. That's it. Bye.